start then. Small exponent attack. This type of attacks, what we will generally see in RSA, mainly because the term small exponent here indicates the value of e what we select. Okay, in RSA algorithm, the value of e, which is part of encryption key, will going to be selected, say, by comparing that with the file. Here, so we are selecting the value of e based on the value of file. So the condition is GCD of these two must be equal to 1, or they must be relatively prime, one and the same. Okay, so normally there will be a tendency of selecting e value smaller. There are many reasons for it. Okay, so it is a tendency of selecting e value small. Okay, because it is the first choice, so e has to be selected first. Naturally, during the process we select a smaller value of e. So this smaller value of smaller e selection value will create a problem, or it will provide a, say, window of opportunity for the hackers to break RSA. It will provide a opportunity for hackers to break the RSA. Now, to analyze this, okay, how exactly these small exponents will go to create a problem. Okay, for that reason, to analyze that, what I will do is I will assume that some person A, okay, is sending a message to B, C, D, and he is sending the same message to all of them. Okay, he is sending the same message to all of them. Okay, with this assumption, we will try to analyze the small exponent attack. Okay, how exactly it is breakable and all. And this is one of the possibility that then naturally whenever he is sending the, say, same message to multiple people in the group. Okay, so that kind of a scenario I have taken and I will try to analyze it. Okay, now here one more assumption that hacker is 3. We started with the assumption that e is equal to 3. Okay, or e is the part of encryption key. With that assumption we'll start. Okay, so to encrypt the message, okay, you know, we need a support of n1 n. So in case of B, the n value is n1. In case of C, n value is n2. In case of D, the n value is n3. How exactly these values are obtained? It is by multiplying these P and Q. Okay, so these P and Q are large prime numbers. Okay, so here too it is P2, Q2, and it is P3, Q3. Okay, so all these are prime numbers. Okay, naturally, if we send the same messages with this arrangement, okay, and see, since it is E is a choice, okay, so it is 3, encryption key is 3, so he has to use 3 with all these messages. So if he uses this with all these messages, okay, so what will go to be landed up is, so we will going to land up in some ciphertext C1, C2, C3. Yes, ciphertext C1, C2, C3, which is obtained by, say, m raised to q mod. The assumption is this is my small exponent. For understanding reason, I have taken a 3. So normally the smaller values which we use, that is required to be substituted over here. Okay, mod n1 m cube mod n2 and n cube mod n3. Now you try to compare these three equations. Okay, if these three are relatively prime, okay, just recall your say Chinese remainder theorem. So the equations look more or less same as that of Chinese remainder theorem. Okay, we are talking about the ciphertext C1, C2, C3, which can be obtained with the help of Chinese remainder theorem. That is, n is calculated by using n1, n2 and n3. So then n1, n2 N3 they are calculated. Yes. So based on that, it is possible to solve these three simultaneous equations with the help of which it is possible to know the value of message. Okay. So provided here one more thing is that we have, say, the assumption is that hacker has an access to this C1, C2, C3. He knows these three values. He is not aware what is the message. Okay, but he is also aware that the exponent that is used is 3. With these assumptions, we have continued. Okay, we continued. Since this N1 is available in the public domain, okay, easy to do this equation. Okay, E and N1, okay, because they are encryption part, encryption keys. Okay, they are available in the public domain, so he uses them. Okay, since this message is unknown to him, ciphertext is known to him. Ciphertext is known to him. Okay, because he is hacking this ciphertext which is getting transmitted to these people. This message gets converted to ciphertext. Okay, so this ciphertext has an access for hacker. Hacker can hack these things. Okay, he knows these things. So then these three simultaneous equations are nothing but or can be solved with the help of Chinese remainder theorem. So once if you apply Chinese remainder theorem, this unknown quantity can be obtained with the help of the values what you substitute over here. Okay, so it is easy for a hacker to break or to obtain the message that is transmitted. Okay, so once he knows what is C1, C2, C3, okay, applying a Chinese remainder theorem, he can break. So this is what we call as a small. It is possible because smaller exponent, smaller e values. Okay. Mainly because of the smaller e values. Now, how to overcome these type of a problem? Okay. So this is also kind of an attack that what we have discussed in the last class. Okay. So how to say overcome these issues? Okay. For that, we use a technique known as public key cryptography standard. Public key cryptography standard, PKCS. Public key cryptography standard. Okay, PKCS. So normally this particular technique is applicable to both exponent as well as message. Okay, now when your message block size is smaller, okay, that time also this technique is applicable to it, and when the exponent size is small, so in that situation also we use this technique. Yes. So what exactly this technique says? The technique is simple. Yes. So here what we do is we talk of, say, padding. We talk of application of a pad. Okay. What exactly this padding means? Okay. Say with the assumption that my message or my plain text, okay, which is of smaller size, to this I am going to pad some value over here. Okay, same is the case with exponent. If this is an exponent, if this is a smaller exponent, we talk of padding some additional values. Okay, so that it should be visible as a bigger value to the hackers, which will hide the information that actually E has. Okay, so to hide what is the value of M or what is the value of E, if they are smaller, in that case normally we bring it to some standard length. Okay, so for that we use a technique known as public key cryptography standard, PKCS. Okay, so what exactly happens in this PKCS? Okay, as I said, we talk of, say, padding some values. Okay, some randomly selected some randomly selected non-zero bytes will going to be padded over here. Non-zero values, okay, will be say padded over there. Okay, how exactly the padding will going to be done? Okay, you see, it will be like this: 0 0 0 2, then a pad, then 0 0. Okay, then a pad, then 0 0. Okay, so the padding will be done in this way. This is what is the structure. So when it comes to the pad, it is some kind of a random number. Okay, you are begin with this, you are ending with this, but in between some random non-zero values will go to be padded. Some random non-zero values will go to be padded. Okay, say the rule says that there has to be at least 8 random non-zero bytes. Okay, is added over there. Okay, 2 plus 8, 10, 10 plus 1, 11. So 11 bytes are going to be padded. Okay, so usually it is a random bytes. It is some kind of a random bytes. So basically, one of such standard is developed by PKCS laboratory for RSA. So we call it as PKCS #1. Okay. So this is one of the 15 standards. Okay, one of the 15 standards. According to this standard, you have to pad the values in this fashion. Now this is what is the standard method. So that is the reason we say it as a standard one. So it says that you have to pad 8 non-zero random bytes over here and 3 bytes. Okay, they are fixed. They are fixed. No matter whether it is E or M. So padding idea will go to mean same. Okay. Padding idea will go to be remain same for both E and P. Okay. So this is how the RSA tries to hide smaller sized message and smaller size E values. Any doubt regarding this? Any doubt regarding this? Please put some message. Please put some message. Please put some message regarding all of you are there. Simply putting message and vanished or what? Because the viewers it is showing is 0. Are you there? What no Omkar? Please come on WhatsApp. Please come on WhatsApp. Please come on WhatsApp. Okay. All So this completes the portion of, RSA. Okay. So RSA discussion is over. If you had anything to ask, okay, I'll be over here. I'll give you 2 minutes time. If you have anything to ask, please come on WhatsApp and say put your doubts. Else, I'll discuss one simple example if possible. Okay, or otherwise we'll quit the class. Choice is yours. Please put the message in the WhatsApp. Okay, fine it is. Then I'll give one example for discussion. You just try that and say submit an answer to me in tomorrow's class. Okay, so I'll give you one simple example for, say, as a kind of a so homework task. So don't try to write this in a assignment. First we'll see whether you will going to get a correct answer or not. So then we'll decide whether to be this will be a part of your, say, assignment or not. Okay, so I'm going to give you one simple question. Please go through it, yes, and try to answer the question. Say first I'll write that question over here. You attempt this question today. Okay, then we will end the class. Okay, the modulus, yes, in implementation of RSA is implementation of RSA is 143. Is 143. What is the smallest value of valid encryption key? First question. What is the smallest value of encryption key? Valid encryption key. And second is corresponding decryption key. Corresponding decryption key. Yes. Okay. So this you try to solve. Okay. So just I wanted to demonstrate you. If you know how to factorize this, okay, so then it is easy for you to get the value of E. Normally what happens, E will be in a public domain. Okay, E and N, say they are public key. So once if you are able to factorize this, okay, then find the value of D. So the task is, first you need to find P and Q. Once if you get a P and Q, then find phi n. Once if you get a phi n, inverse, say once if you get a phi n, Okay, so it is p minus 1 q minus 1. With the help of that, it is possible to obtain encryption key, and with the help of say in encryption key, decryption key is possible to be obtained. So this calculation you think and do. Okay, first you attempt it and post the answer in WhatsApp group. Post the answer in WhatsApp group. Okay, so today I will end the discussion over here, because from next class onwards I am going to start with hashing functions. Okay, that is a new topic. Fine. So cryptographic hash. Okay, that will be the next topic which I am going to discuss in the next class. Okay. If you had any doubt or any problems, you are free to ask. Okay. So now I will end the stream. Take care. I hope